Hello. Hi guys, good morning. Welcome back to new video. Ki hal chal? I hope you're doing good. In this, we're going to see find elements in a contaminated binary tree. So they're simply seeing a binary tree, a tree having at most two nodes. That is called a binary tree. This is given to us, right? With the following rules. What's the rule like? That the root value should always be a zero. Okay. Then for any tree node where the value is there and let's say the value is x, and if there is a left child, which means the left child is not null, then the left value will be 2 into x plus 1. So obviously if we see that there's a left node, if there is, then the value will be 2 into 0 plus 1, which is 1. If there is a right child, again whenever I am mentioning if there is, right, then the value will be 2 into 0 plus 2, and same way it will keep on proceeding forward. If there is a left child, then it will be 2 into 1 plus 1, which is 3. If there is a right child, it will be 2 into 1 plus 2, 4. So on and so forth. This is how we can make it. Now they are saying that given now the binary tree is contaminated, which means that all the node values have been changed to -1. So this tree was built at some point in time, but now it is contaminated, which means now they have changed it all to -1, -1, -1, -1, -1, right? And again, it is possible that the left child would not have been there at all, right? So this is the contaminated tree which is given to us. I have to implement a find element class which will say, okay, I will give you a root node of this contaminated binary tree, which is this specific tree I will give you, where you know a node exists or not, right? Because again, obviously, if a node doesn't exist, its left child will be null, or maybe any child will be null if it doesn't exist. But the values you don't know. The values you don't know. And you have another function you have to implement, that is that returns true if this target value exists in this specific tree. Now obviously one very basic thing which comes to mind is that contaminated tree helps me to just identify if a node exists there or not. So what I can do, I can just start building the tree. I know the root node will always be a 0. I will check my contaminated tree and will say that if it has a left child, okay, make a left child. And how to get that? 2 into 0 plus 1, right? Put it a 1. If I see it has a right child, yes, it has a right child. Okay, 2 into 0 plus 2, okay. Then I go to 1. Do it has a left child? No, it does not. Do it have a right child? Yes, it does have. Okay, if it has, then what is the value? 2 into 1 plus 1, which is nothing but 3. Sorry, 2 into its right child, so 2 into x plus 2, which is 2 into 1 plus 2, which is nothing but 4. So this is how I have built my original tree back from the contaminated tree. Now the question is that at every function call, which is find call, you have to find the target exists there or not. So the first step is how will you build this tree from, the contaminated tree to the original tree? How will you build it? You can build it via simple graph traversal, either a BFS or a DFS. That's as basic as it. Now, as a next step, again, if you don't know what it is, just simply make sure that you have practiced the tree problems, simple tree problems. Just come on to the practice problem sheet. In that, you will find a numerous tree problems for you to practice. Easy, medium, hard, all categories. Now, coming on back, we realized that the target I have to find. So one naive way is at every function call of target, I can do an entire tree traversal and find out. Do I have a 3 here? Oh, no. Do I have a 4 here? Oh, yes. So for every function call, I can do an entire tree traversal, which will take O of n time considering I have, this entire tree having n nodes. This will take O of n time considering I do entire tree traversal at every function call. But is it needed? Obviously not, because I have, firstly, this is the contaminated tree given to me. When this entire tree is already given and there is no change in the tree nodes after it is built, because again, contaminated tree is built, I just have to refine the tree and get me the tree with the nodes. Now there is no change in nodes, right? So what I can do, okay, I can simply make sure that I will put all these nodes into a data structure that data structure can help me find something in O of 1 time. And what is that data structure? This is nothing but unordered map or unordered set. I can use an unordered map or an unordered set just to know that is these values exist in my data structure or not. And how I got these values? I got these values by traversing on my this specific binary tree. And this I can do again, putting all these values in the data structure. I can do while I am building the tree itself, or I can say while I'm refining my contaminated tree itself. Cool. And with that, it will take now O of 1 time. So what we did finally, we did that whenever we have the find elements, right, we will be given a contaminated tree. I will simply go and make sure, okay, from this contaminated tree, keep on building a refined tree. How I'll build it? Okay, root is this. There's no left child. Right child is this. Okay, the tree is finished. And while I'm building a refined tree, I will also be keep on putting these nodes inside data structure, which is unordered set. Ultimately, I will ask find of 1. Not there. Okay, false. Find of 2. Yes, there. Okay, true. Thus, building the tree would take O of n time and O of n space, which means this find element will take O of n time and O of n space. Sorry, this find elements, yeah, will take O of n time and n space because this is refining a tree, but this find will take just O of 1 time. Obviously, space is already taken by this O of n space, which is building, your tree will have its recursive depth and all that stuff, along with, you will have to take a unordered set just for maintenance of all the keys. Same way, if I come on to here, I will say this will be 0, left will be 1, right will be 2, left will be 3, right will be 4. That's how my tree is built. And while I was building it via simple DFS, I could have built it. I would have also put all these nodes inside a data structure. Now find has just built this tree and also made sure that put all the keys inside the unordered set. Now I will have find of 1. Yes, it is there. Okay, true. Find of 3. Yes, it is there. True. Find of 5. No, it's not there. Okay, false. And thus each operation took O of 1 time. Same way for last, it will be 0, then I have 2, then I have 5 because it's a left child, then I have 11. I just simply build that because I always know it will start always from 0, and that's how it is done. Let's see the code. It's exactly simple DFS, although it could have been done by simple BFS as well, but still, DFS is much more simpler, easy, short, and concise. Whenever I call the constructor, I will call a recover tree. This will make sure that I am override, just building the corresponding tree with the overridden values of the tree and also putting up all the values in an unordered set called as recovered values. So what I will do, a simple traversal saying if the node is null, simply return it, right? And then I will start from here and will override the value. Again, starting off, root node having the 0 value. Override it. Make sure to put all these values inside my data structure, which is recovered unordered set. And then making sure that if there is a left child, just simply go and call the left child and 2 into values plus 1, exactly same as what is given in the question. Right child, 2 into values plus 2. And if it is null, then obviously it will come here and obviously it will return from here itself. If not, then you are good to go. You will simply place the values, or you can say override the values. And with that, your tree will be built or refined or recovered. And when the tree is refined, recovered, at the same point, you had also all the values in your data structure, which is recovered values. You will simply call if this target is there. If yes, then true. If not, then false. And that's how you can simply solve it. Time will be taken O of n. Space will be taken again. Time for this operation will be O of n. Space of this operation will again be O of n. In total, the space also will be O of n. Here the time will be O of 1. And again, you can say space as O of n, but this is already covered here. So space, I can say as O of 1. Cool. I hope you guys got it. Bye bye. Take care. Make sure that you practice trees. It's an easy category question marked as medium, but still. Bye bye. Take care.